Hello, everyone, and good day, good morning, good day, good afternoon, good evening, or good night, wherever you are in the world. And we are back again here on the stream for another lesson. And yep, I'm gonna go into the classroom now. We're still doing some special relativity, I think, but I still hadn't received anything to do today. But either way, let's see what it is. We'll update it accordingly. All right, let me get into classroom now. And I might as well set up the board. Hold on. There you go. Oh, let's change the board real quick. This is the wrong word. Yes, these have been some of my other students, in case you're wondering. Of course, uh, let's just wait for that to load. Okay, there we go. Okay, I think we're still gonna do the same discussions from before. Oh, there, we just got some new ones here. Let's get ready. I think 5 questions for today. All right. Uh, okay. All right.
Hello.
Hello, Gita, and good day, I guess. How
Yes.
was? Yep. All right. How was everything today?
It's good. How
Good.
about you?
Doing great here. I'll be traveling tomorrow, actually, by the way.
Okay.
Uh, so
So,
so for the lesson schedule for tomorrow, do you think we can either move that to another day on Monday? Because it's our school break right now, actually.
right.
So I'll be traveling tomorrow, and I'll be available evening where I'm gonna be. So that's still gonna be more or less the same time over there. Okay, is that fine?
Okay. But I mean, if it's too much for tomorrow, like if you're busy, we can reschedule it.
It's fine with for tomorrow. Yeah, I guess we really have to schedule it because I'm not so sure
Yeah.
if I can make it on time to my flight tomorrow if we have the lesson. All
Oh,
right. But
right,
anyway,
right.
don't
Yeah.
worry too much about it because the airport is half an hour from here,
Uh,
so it shouldn't be too much of an issue. All right. So is
um,
Monday okay
I
with you
can
though?
reschedule it. Yeah. But it's also about 4 p.m. Would that be
4
okay?
p.m. your
Here.
side. Sure, no,
Would that
no
make
worries.
sense?
No worries. Just let me know and I'll be the one to schedule it because that's beyond my availability. But since it's our term break, I can make accommodations for that. But I should be the one to move it so it's ready. Okay.
Okay.
All right. So 4 p.m. your side on Monday. So I'll move tomorrow's lesson. Okay. All right.
Okay.
You sent over a few more questions. Oh, there's one you sent before, and then there's a couple here. All right, so let's do the one you sent before. Okay.
Okay.
All right. Um, here we go. It's not copying, is it? Okay, let's do that again. There we go. Okay. Um, excuse me. Okay. So here's a couple of questions here. As a demo for the legitimacy of adding fourth coordinate here, consider someone who's crossing a highway. Both the person and the van have the same spatial coordinates at some time, but they don't collide because they have uh different time coordinates, and then the second part there is okay. I'm not so sure what this 37 is unless it's really just an example as mentioned here. Okay.
Yeah.
Okay. But I think you'd like to have this like explained a little bit, right?
Yeah, and I don't know how to draw the space-time diagram, I
Okay.
guess.
Now in this case, for number 37, the space-time diagram is gonna be a bit difficult to um draw because of the three-dimensional nature of the space XYZ given here. Okay.
Yeah.
So what we'll do instead is we'll just consider X and we'll for now ignore the Y and Z coordinates for now. Okay. So
Mhm.
that's why we have the space-time diagrams, right? Now, which one of these objects is moving at some time? Okay. It doesn't really matter. What this basically means is if I'm gonna use blue for the van and orange here for this person, okay, for the traveler, the person. Let's go back to the van. It says here that the van have at some time the same spatial coordinates, right? Okay. What
Yeah.
this means is the van could be here. If this was your X and this was your CT, right? The van could be here. But the person could be some other time but same position. So that person could be there. That's a possibility. Another possibility is this person was here. Another possibility is this person was here. And whatever other positions. We could have a different coordinate for the van as well. For example, let's erase that. The van's position on the space-time diagram could be here, or it could be here, or whatever. Okay? So any of those positions, in these cases, this simply means same position, different times.
Wait, sorry.
Go
Can I
ahead.
ask something?
Go ahead.
Um, this diagram is not the same as the Minkowski.
It is.
Minkowski.
It is the same diagram. It's still a Minkowski space-time diagram.
And then do we draw the line of the light?
We don't have to, but it would be a good idea if you did. So, um, let's put that in there. Okay, let's use red for that. So, let's just say for now that that's our light. This is our light cone, right?
And would it mean that then the car is moving faster than the speed of light?
No, it doesn't mean anything because as you see here, there's no line. It's just a point. The car would be
Right.
moving faster than light if its light cone was that. Okay.
Mhm.
What this means though is if we have another observer here, then this observer doesn't see this van. That's all it means.
Why?
Because it's outside of the light cone. But um at least at this time, okay? But if so at this time, let me say that again just to clarify that. At this time, um so how do you say that? Okay. So at t equals 0 for red, okay? For red, he doesn't red does not see blue, okay? See blue, okay? That's what it means because it's outside of the light cone. But red sees orange, okay?
So the light line was always drawn in terms of the observer and what they see.
Yeah, in terms of the observer. So if you want to turn blue into the observer, then you would have to draw a new set of lines for blue, and I'm going to use a new set of do that there and there, and then you're gonna have to draw the light cone for blue again. Okay. So in this
How do we
case,
know?
so go ahead. What's the question?
Sorry. How do we know if we can, how wide we can make it or how narrow?
It's always going to be the same angles. Always going to be 45 degrees from the x-axis.
Okay.
Okay. All right. So that's in terms of the light cone and what it means if you interpret the motion, the positions. But remember, at this point, let's just assume that our blue object is not moving, right? If our blue
Yeah.
object isn't moving, then how would its let's just draw the coordinates for blue for now without those um transformations just yet. So blue's coordinates would look like this. And so the light cone would be like that. Okay? But I won't draw the light cone. So what I'll draw this part of the light cone though. So what does this mean? Blue does not see red because it's outside of the light cone at the moment, right? But it actually could see orange. Okay? Because it's within the light cone. But if we take a look at orange's light cone right now, orange's light cone, we draw again the coordinate axis for orange like that. We can do the past light cone as well like that, right? So in this case, orange still sees blue. But the weird thing about and here's the thing, orange also sees red. And that's not weird because red sees orange eventually, right? Okay. Um
Uh,
okay,
Wait, sorry.
go ahead.
These light cones, like, do they mean like our spectrum, like what we see with our
No,
eyes, or
no.
what do they?
These light cones just represent the limits at which we can observe something. Because remember, the speed of light is the speed limit of relativity, right?
Yeah.
Okay, so these light cones represent that limit, that speed limit. Nothing can our current interpretation is nothing can travel faster than light, or if it does, it's gonna be beyond the light cone, and we are not able to observe those. Okay, now let's do another quick one here. Let's continue with this example here. Draw a space-time diagram. So draw the space-time diagram for a particle at rest and for a particle traveling in the positive x direction. Let's keep the space-time diagram separate first. Okay. So for our first object, remember, something not moving does not mean it's only in space. It's not that it's not moving, right? But if you think about it, everything moves through time. Nothing is frozen in
Yeah.
time, right? So for a particle at rest, well, what's its space-time diagram? It's gonna stay at the constant x, but it's ct, but on ct it moves, right? So
Yeah.
what would you expect it to look like? Would it look like a horizontal line, a vertical line, or some sort of diagonal line?
Just vertical.
Right. Now, correct. It's gonna be vertical, but it could be any vertical line. Okay. So all of these would be valid space-time diagrams for a particle at rest. However, the special thing about that first one is this is at rest in its own in inertial reference frame. Okay? So
And
go ahead. What you want to say here?
sorry. And depending on where we draw the X, is that where it is in respect to the other observer?
Mm-hmm. Uh-huh. So what does these mean? These two other lines, they are at rest, but it's not the observer's reference frame. These are at rest relative to observer. Okay? I'll use right here.
To the other observer?
At rest relative to observer, to the observer. Okay? And this is the actual observer, its own reference frame, so this is the observer. Okay,
Mm,
so
but isn't every sorry,
go ahead.
isn't every observer when they're at rest they're at zero
Okay,
X?
I think it's best done like this. You're right there, I'm right here, but who's my observer? I'm my own observer, right? And you're your own
Yeah.
observer, but we're both at rest right now, right? So from
Yeah.
my reference frame, I'm this one, from my reference frame, and you're this. Let's undo that.
Yeah.
Okay. Okay. So again, from my reference frame, I'm this thing, and from my reference frame, this is you. Okay. Now I'm gonna draw another set of another axis here, just to illustrate the point. Okay. Now in this case, this is me. This is you, right? Now if we switch it over so that this is you, that's you at rest, but I will be here, going that way. This is me. Okay.
Yeah.
All right. So again, what you put on that CT, or what you put on the origin, is always the observer of that reference frame. Any other thing that is stationary relative to you as the observer, you put somewhere else, because you can never be in the same place, in a manner of speaking. Okay.
Mhm.
Okay. So is that clear on how to draw the space-time diagram here?
Yes.
Great. Okay. So how about the particle moving in a positive x direction? So let's do the second one. How will we draw that other one? So we have this, our space-time diagram. This is your x and this is your ct. Um, okay. So a particle moving in a positive x direction, what would its space-time diagram look like? Okay, it's gonna be useful if I do this first. Again, this is the observer, right? The observer is always gonna go like that, right?
Yeah.
Okay. How will a moving object look like in terms of the graph here? Moving in the positive x direction.
Uh, like an x equals y line.
Okay, not quite, but you have the correct idea. It should be something like that. This is the moving object, right? Okay. Remember, if you do x equals y line, this is the um, this is the light cone. Okay. So basically, you're gonna have to draw that. In other words, the only thing that should be on this line is anything that moves at the speed of light. That includes light itself, whatever other things we know that move at the speed of light. Okay.
Yeah.
Okay. All right. But aside from mentioning this, that idea is correct. It should be going up like that. Okay. How does this look like from the moving object's point of view? If the moving object's point of view, how will this look like? So
Mm.
let's use the notation now, ct prime and x prime, right? In fact, let's put here. I forgot to put that here. Let's just put here x prime, ct prime. Okay. So going back here, how will this moving object's um world line look like?
Mm, the same.
That not quite.
Yeah.
Remember, we're looking at the prime now, so we're looking at this object here. Let's call this object A. Okay. From A's point of view, its word line is always like that again. This is A. Okay.
Oh, right.
Right. Now, you, let's call the observer B. How's your line gonna look like as the observer according to A?
They're gonna be seem like they're moving in the opposite direction
Correct. So
that we
something
were.
like that. Okay. So this is gonna be B. Okay. Great. All right. You're kind of getting how to read them. Great. Okay. Um. Okay. Let's see, which question can we do next? Okay. Let's do this question here. Uh. Okay. Okay, so the question here is, this is the question about Simon and Lucinda, where Simon's on a railway carriage traveling in a straight line with a uniform speed, and Linda is standing on the ground by the track. There's a window on each end. Simon determines the position to be at the midpoint. Okay, his position to be there. At the instant that Simon and Lucinda are opposite each other, a bird lands at A on the carriage and the other one at speed. Lucinda determines that the two birds land simultaneously. All right, this is a good example. Remember last week we kind of mentioned about simultaneity.
Yeah.
Okay, so it just says, we'll just go to what it means first before we solve this. Okay, simultaneity in relativity, it's like this. For most of for daily experiences, if something happened, if two things rather happen at the same time for me, it should happen at the same time for you too, right? So for
Mm-hmm.
example, when I clap my hand, clapping my hand would be wrong. If I snap my fingers at the same time, I would say they snap at the same time, and you would also say they snap at the same time, right? But once we hit relativistic speeds, let's say that I'm moving and I snap my fingers together, you will say that I did not. I snapped one finger before the other, according to you. Okay. Now we there are again two ways to do simultaneity. We can do the solution, we can do the calculation, or we can use space-time diagrams for it. Okay. We'll do the calculation first because it's the easier one to do. Okay. All right. So taking a look here now, who says that Lucinda? Who says that the two birds are they land simultaneously? It's Lucinda, right? So state and explain whether Simon will observe the landings to be simultaneous. The answer here would only be yes or no, simultaneous or not simultaneous. And then for the explanation, we need to do some calculations. Okay.
Okay.
All right. Um, let's go through how. Let's go through how Lucinda determines that they happen at the same time, right? So, L, our S reference frame would be Lucinda. Okay. Now, according to Lucinda's reference frame, okay, the bird. So land. Let's just instead of just saying bird, let's say that the signal from the bird reaches her eyes like that. Similarly, the signal from her eyes from the other side also reach her like this, right?
Mm-hmm.
Okay. So in other words, for Lucinda to see the two birds land simultaneously, there are two possibilities. Either this distance is equal to this distance, so x in y. Let's do x1 and x2 for now. X2 and x1 should be equal, and therefore the light should reach Lucinda at the same time, or the light the light got emitted sometime first, and then could be like this. Okay, so that's the middle, and it's here. So let's call this again. Let's call these A and B. Okay, so which light source here, according to this part, A and B um, emit light together, right? And why do we have to go back to light? Because Lucinda has to see those birds. So seeing involves light. Okay, so in other words, A and B emit light at the same time. Okay, at exactly the same time. So that's one possibility for Lucinda, right? The other possibility, though, is that sorry, A must have um, emitted light first, right?
Why?
Okay. Well, I gotta ask you, which light has a longer travel distance, A or B, from this other possibility?
Uh, A.
A, right? Because A has a longer travel distance, right? Okay. Now, this is so far, we've only looked at two possibilities. We haven't even included the speed just yet. We can put the third possibility here, wherein it's kind of like the opposite case. A is here, B is here. That's the halfway point, and then Lucinda would be here, right? So in this case, it's similar to the second case, but B must emit light first, right?
But isn't she positioned in the middle?
That's the thing. We're looking at the possibilities first, and then we'll see what actually happened. Okay?
Okay.
Because even though it's kind of mentioned here that she's positioned in the middle, you have to take the fact that light has to travel and take some time to travel, right?
Yeah.
So, in other words, we have to consider the velocity now, so or the speed. So if we put the speed in like this, and it's all gonna have that speed v, right? Which of these is actually the most likely scenario? Again, let's assume that this speed v is close to the speed of light, so it's gonna be observable. Okay, so which one of these is the most likely scenario? So that what happens later is that the light, when the light reaches Lucinda, Simon's right in the middle. When A happens, the when it's the first case, what happens is they're no longer aligned like this when the light hits Lucinda's eyes, right? Similarly here for B, um, this pretty much means that here, um, what's his name here? Simon's already here, right? So the only possibility where Simon coincides with Lucinda is A.
So there can be like an instance where Simon is in front of her
Yes.
and the light travels the same.
Mm-hmm. But again, the only instance that's possible is B because the train is also traveling. If the train wasn't traveling or is traveling very slowly compared to light, then it's gonna be the first case. Okay.
Hmm.
Okay. I know that's a lot to take in. Uh,
I mean,
Go ahead.
we did this in class, but I just didn't understand because there must be like an instance when the train is right in front of Lucinda.
Mm-hmm.
So it was obey the first one. I know it's moving, but it's also, I mean, there's an
Right.
instance when
Okay.
it's right in front.
Um, you know what? I think I'm gonna look for okay. Yeah, that's the thing, because again, it's very common. The common experiences we have is it must be A, right? Because that's the instance wherein Simon and Lucinda are right in front of each other. Okay, but you have to also remember here that because light has to travel a certain distance, and they have to travel again, since this is longer, since the path of A is longer than the path of B, that means this must take more time, right? So if we put a stopwatch here and it happens 0 sec, let's just not stopwatch. Let's say that this happens 10 seconds, at t equals 10 seconds, right? So when was the
Mhm.
light released here? The time released, let's say that the time it took 0 seconds, right? So the time from A to Lucinda is gonna be a total of 10 seconds, right? But because B's travel time is shorter, when was this released? Is it also 0 seconds or some other time between those two?
A bit later.
A bit later. So let's just say, for argument's sake, let's say that this is 4 seconds, right? So this takes 10 seconds to travel. This takes 6 seconds to travel. Okay. So just by reasoning it out first from Linda's point of view, or from Linda's reference frame, So what we're looking at here is not the actual, um, I wouldn't say the interval of time, but I would say when it started. So A started first, you see, because than B, because T because A started at T equals 0 seconds and B started at 4 seconds. So as the train is traveling, what does Linda perceive? As the train is traveling, remember the light's also traveling towards here, wherever the train is, right? And once the light hits Lucinda's eyes, she will see that the two things, A and B, emitted light at well, she receives the light signal at the same time. I think that's the best word to do it. She receives light at the same time, right?
Yeah.
Okay. So it's all about the difference between receiving the light or receiving the signal and when was the signal actually emitted. Okay.
So, because the train is traveling, B is closer to her, and then A needs more time to travel.
Mm-hmm.
But what if we? But it seems like we picked an instance when the train has not reached her, like parallelly yet.
Okay. Now, what does okay? So that's a good question. So why do we have to pick this instance instead of having that train right in front of her when it happens, right? Um,
Yeah.
the best way for you to kind of see this is, well, okay, let me go back to regular camera for now.
Mm-hmm.
Okay, what can I use to simulate our train? Okay, I have a small notebook here. We'll simulate the train with that. Okay.
Okay.
Okay. So this is the train. What will I use to simulate Lucille? Okay, I have a battery here. Let's see if this is gonna work. Okay, that's gonna work. All right. So again, there we go. You can see that, right? Okay. So
Yeah.
again, so what's happening here? This releases. Nah, it's not so good of a. There we go. There we go. So at this point we know. So we already know this releases the light first and that, right? So at
Yeah.
this point, what's happening here is this gets emitted first and then that gets emitted next, right? So something like this again. Emit, emit, reach together, right? Now,
Yeah.
as that happens though, the train is also moving. So, um, so what's gonna happen? Once, imagine it like this. Imagine that the light here turns on, the light here turns on, then turns off, just for an instant. Okay. Same thing
Mhm.
here. The light turns on for an instant, then turns off. So that's the idea. So, tur- so what's gonna happen here? Where what's his name? What's his name again? On the example, sorry. Let me
Uh,
see.
Lucinda and
Simon.
who?
Okay. So where's Simon on the train? Simon's here in the train, right? Okay. So the
Yeah.
idea here is, let's say that Simon is constantly emitting light right here, right? So if Simon's constantly emitting light, what does Lucille see? Lucille sees Simon, right? But let's imagine that Simon also only starts emitting light when the two birds land. So what happens? All of them what happens here? This turns on first. This end turns on first, then this, right? So I think I'll just do it like that. It's shorter. Uh, okay. I think okay. Not gonna work. Yeah, that's gonna be better. So what's gonna happen here? Okay. So what's gonna happen here? Light gets emitted from A first, right? Then B emits light. So okay. What happens with
Mhm.
Simon though? Simon, when this happens, basically Simon also emits his light after A, because it's the same idea. Instead of looking at the ends, we're looking at where A is and where Simon is, right? So when Simon is releasing light here for Lucille to see, when Lucille actually sees them Lucille sees them like this, what actually happened was the light got emitted here, the light got emitted here for Simon, and the light got emitted here for B. See, as they travel, emit, emit, emit. So the effect is, according to Lucille, the three things happen at the same time. Okay.
Oh, because the first time she gets the light from him,
Yep.
he's actually already moved on a little bit because the speed of light he's moving with.
Yes,
Oh, okay.
exactly. Right. So it's the same idea with the two light sources. Okay. Or in our
Okay.
case, the birds is the same idea. Now, having said that, according to Simon, which one emitted the light first? So let's do the same idea. We know. So let's go back to the notebook now. So we know that which one is it here? From your point of view, it's gonna be here first, right? So we know that this side of the train emits the light first, then this, right?
Hmm.
But if they okay, so we know that for again, just looking from a no, from a logical perspective, not from what actually is observed, right? But if we use that same logic that this goes on first before this, the light on this end goes on before the light on this end, and Simon's right in the middle. According to Simon, which light will he receive first? Is it the A or is it B? Remember that A emits the
A.
light first, right? So according to Simon, which one happens first? A first.
A. Okay.
Okay. So that's the logical explanation using relativity and the speed of light. Okay.
Yeah.
All right. Does that make sense now? Because I know that's kind of a lot to take in.
Yeah, but it makes more sense than it did before.
All right. Great. Okay. So So we've basically just done this now. We've stated and explained whether Simon will observe the landings simultaneously. No. The answer is no. Which will he observe first? A
A.
first. Okay. All right. Example show that delta x prime equals this for this example. Uh, okay. This is actually deriving something. Okay. X prime, which is gonna be x prime. Uh, okay. Let's kind of look at this again from the two reference frames S and S prime, right? So according to S, let's put S here to be Simon this time, okay? Okay. Now, if Simon's in the train has a length L, right? Right? Um, and this time, let's put Simon here on the inside. And here on the inside, he has a light source, and that light travels back and forth the train. So what's according to the speed of light, he measures this with a time t, okay, or delta t rather, okay. So
Yeah.
according to Simon, what's L gonna be? That's just gonna be simply c delta t, right?
Yeah.
Okay, and we instead of saying L now, let's say that this is x1, this is the initial position x0, and this is a position x, right? So L, we can also say that L is equal to some delta x, right?
Yeah.
So I'm going to just write this down now. Instead of saying this is L, I'm just going to write that down now as delta x. Okay. So simple enough from Simon's reference frame, right? But let's take a look at this from S prime. Okay. Or this is going to be Lucille again. Lucinda, rather. Okay. So according to
Mhm.
Lucinda, the train was initially here. Then it travels a little distance, and I'm just going to draw the train here. Okay. Actually, no, I'm not. Let's adjust it a bit. Let's put the train here. So after this is t equal t prime equals 0, and this is equal to some value t prime, right?
Yeah.
Okay. So in this time, uh, remember that the light has to travel that way and back, right? Okay. Now, according to this though, basically, what do we? There's something I missed. Oh, there should be an over 2 here. Okay, there we go. That's just something I missed. So so the light still has to travel that way, and then it's gonna have to travel back the other way because of the mirror, right? So in this case, let's just do it like this first. It has to travel back and forth. So our delta t prime, that's pretty easy. That's just there already, right? So we know that. And here's the thing though. What is delta what is gonna be, this is x prime 0, and this is gonna be x prime. What's gonna be delta x prime here?
Mm,
We use the same idea here.
C
C
C change in T dash.
all over 2, right?
Yeah.
Okay, so we kind of already see that this distance, that the length of the train according to s prime is going to be different. At least right now it's gonna be different, right?
Yeah.
Okay, but I gotta ask you, if you think about this, this is the length, right? Let's not do it like that. Where is the actual length of the train? Okay, in this case, we need to kind of look at an intermediate section right here, right? Okay, so in this case, this is where this is gonna be where the light hits. Okay, um, shall we do it like this? I just had a thought. Should we actually do it like this? Yeah, we have to. Okay. Now, you can already see that we can just change that, we can just express here that c is equal to 2 delta x over delta t, right? So we can substitute it right in here right away. Okay.
Yeah.
All right. But what are we gonna do? It's going to be 2 delta x delta t prime all over delta t, right? There's a 2 here again, so that cancels out. What do we get here? X delta t and x and delta t prime. We can now express this delta t prime in terms of, okay, in terms of
Sorry.
go ahead, in terms of gamma. I think we're
No,
hold.
it was just the phone ringing.
Okay, all right. I'm just okay. Hold on. I'm just wondering about this. I think we're going the long way about this. Okay.
Mm-hmm.
All right. I think. Yeah. I think let's simplify this a bit. Let's. Well, hold on. We can't really do it like that. We need to make it go back. The delta. Okay. Oh, right. I forgot that this has a velocity v. That's the thing we forgot here. There's a velocity v, right? According to s prime. The v is going that way. Okay. So if you think about it further, then that means that okay, that this distance here is v delta t, right? There we go. That's the distance there. So basically the light has to travel forward and backward, but it has to take into account this v delta t, right? Okay, so that
Yeah.
for you to account that v delta t there, I'll just erase this part now. for you to account for that v delta t, you're gonna have to subtract that from the length, because you're going forward. It actually, when it hits like here and then it goes back here, um the light has to kind of travel a little bit. Okay, so in other words, we v delta t has to be removed uh from the length. Okay, okay, so that basically means that our delta x, our length, is actually equal to basically your gamma factor times delta x, right? So we already know this part, it just comes from relativistic solutions, but you're gonna have to also subtract your other length, your delta, your v delta t. Okay, but of course, this being relativity, you still have to put that gamma up there. So that's why we get L equals gamma delta x minus that's L prime, sorry. Okay, so that's also gonna be delta x prime minus v delta t. Okay, all right, I think that's the easier way to show it. All right, but basically that's what happens for length contraction. It gets shorter because it's moving. Okay, now
Okay, yeah.
last thing I want to do simultaneity before we move on to the next three problems there. I want to do space-time diagram for that, for this. Okay, so just as a comparison now.
Mhm.
Okay, so let's do it according to Lucinda. Okay, so again, space-time diagram for Lucinda would be this, right? Right? Let's label that L for Lucinda. That's gonna be CT here, and that's gonna be X, right? Now, according to Lucinda, the two events happen at the same time, but in different spots, right? So we can do that like this. You can basically have a horizontal line, two events. Let's make it a bit more clear. Let's just put the two events here, here. Same time, different times. Same time, different spots, right? But Simon is moving at a speed that's gonna be that's gonna be Simon's speed, right? Okay. Now remember from last time, for space-time diagrams, you can, once you put that once you put the speed of light line here, you can make another axis here for, and this is gonna be Simon's CT prime, right? Okay, and this is gonna be X prime, right? So according to this, let's just see, we can actually just ignore the X prime. Okay, we'll just look at Simon's. So if
And
I'm, yeah,
how can we split up? Sorry.
sorry, go ahead.
How can we split up the x prime Simon's distance and Simon's
Okay, so
CT?
again, so that's gonna be an angle theta for now. There's actually the reason for that is the Lorentz transformation equations. Okay, but basically,
Uh-huh.
if you have an angle there, then that means this is also the same angle for x prime.
Okay.
Okay,
Yeah.
now I'm gonna keep the x prime. I think I'll just keep the x prime there to make it a bit easier. But basically, there are what's gonna happen here? We're gonna have to, our perpendicular, our perpendicular line is going to be something like that. Sorry, it's a bit wrong. Okay, the perpendicular line is going to be something like that. Okay, you see that this line is parallel to this line.
Yeah.
Okay, so this is our perpendicular lines on CT prime. Okay, now the reason we did this diagram is you can see that if we do a parallel line comparison, I'm going to use this blue here. I'm gonna try to make this line go here. Okay, and go here. So according to this, let's go back to what Lucille sees. This is A and this is B. So according to Lucille, A and B occurs at the same time, right? But according to Simon, which one occurs first in this particular space-time diagram? Which one occurs first? According to the CT diagram, which one is higher up in the CT diagram?
B.
B. Okay. So in this particular case, B uh occurs first. Okay. Okay. Now similarly, I'm just gonna do one quick one, but we're not gonna analyze that anymore. If Simon was moving the other way around, which one would happen first?
A.
A would happen first. Okay. Right. Okay. So you're getting that now. All right. Let's do one more problem, and then the next two we'll just do on the next one. Okay.
Okay.
All right. Um, the reason why I wanted to do that is because the next problem I'm picking is this. Okay. Uh. Okay. All right. Here we go. So this is the last problem for today. According to CTs, okay, there are some lights here, and okay, the space-time diagram for this system shows that the lights at rest in a particular reference frame. Okay, so this is the at rest reference frame, and this is the world line of the ship moving towards the landing zone, right?
Yeah.
Okay, so moving. Okay, or one more thing. This is approaching. How do I know it's approaching? Because the speed is negative, so that's like approaching. You can think of it as approaching that way. Okay, so going back here, let's draw the. So okay, so remember what we did earlier. Our theta here, let's just do that. In fact, yeah, let's just do it from this from this light cone line here. If this is our angle theta here, where should our x? If this were x, where's the x prime axis?
Mm,
Should we be above or
of
below?
below.
It should be below, so something like this, right? Okay, and that's also the same theta. This is our x prime, right? Okay, so let's draw those lines again parallel to this. So let's kind of draw it like that to just again show the perpendicular lines, right? Okay. In fact, okay, there we go. I want to show. Have I shared with you that video from YouTube yet showing what's actually happening? That
I don't think so.
Okay, I'll share with you a video later. I want you to watch it. Well, it's not a video; it's a series of videos. Um, so just watch them on your own time later. I'll guide you to which one is the most useful at the moment. Okay. But
Okay,
anyway,
thank you.
all right. So looking here, which one is according to this? Which line is gonna be first?
B.
Okay. So again, so that's something like that, right? So according to this, so again, you're going up this time like that, right? So which lamp do you get to first? Coming from the bottom. Coming from the bottom. So coming from here, go up. So coming from here, go up, yeah? So I'm gonna keep going like so. So which of the lights will we intersect with first? Start.
The line is the one that's crossed with red.
Mm-hmm. Yeah, so that's the one that's with red is just the x prime axis. But remember, these blue lines are just basically just grid lines if you think about it. These are just grid lines. Okay, so I may just do that with the red now. Okay, it's kind of hard to see if I just do it on the screen. Okay, I'll show it to you right here. Oh, that whole time I wasn't showing it. All right.
It's okay. I'm looking at the shared screen.
But actually, it's gonna be easier if you don't look at the shared screen. It's gonna be easier if I actually show you the tablet. Okay. Okay. Let me show you the tablet real quick. You can see that clearly, right? Is it the right way up?
Yes. Yes.
Okay. So. Oh my goodness. Hold on.
Oh.
Give me a few moments. Come on and work. All right, that works. All right. So what we're gonna do now is we know that this is our x-axis, right?
Yeah.
Okay. So what I'm gonna do is just follow that x-axis or x prime axis and basically just move it up, starting from the bottom. Which light do I encounter first?
A.
A, and then
D.
and then
C.
C,
B.
and then B, D. So what's our answer here? A, D, C, B.
C. B.
So our final answer is
D.
D. So, going back to our choices now. Oops. Okay. So ACBD. So our final answer here is D. Okay. All right. All right. So, okay. Is that clear on how we use that angle now to help solve for which one happens first according to a space-time diagram?
Yes.
Okay, clear. All right. So we'll end here. We have two other questions. We'll do that probably on Monday, but we'll see. Okay.
Okay.
All right.
So you can let me know if you're available at 4, but if it's too late, we can also move it.
Wait, hold on. Let me double check that. 4 would be you're 6 hours ahead
10.
of me right now, right?
Yeah. Yeah. I thought I
Yeah.
was behind. I was
Yeah.
behind.
You're almost at 3 and I'm almost at 9 today. So yes, 6 hours. So I'm 6 hours ahead, right?
Yeah.
And then when I travel, that's gonna be another hour additional, so that's 7 hours ahead.
Oh no, that's horrible.
Nah, it's okay. It's fine. I can still manage. Okay.
But
It's
till when are you
I have a 2 week
traveling?
break. I'll only be traveling on Sunday. Then we start our school break now. It's 2 weeks. So basically, yeah, I think it's okay. Cause I do get to sleep very soundly when I travel, so it's fine. Okay.
um.
Don't worry too much about it. I should be able to manage. Okay.
Okay, but even last minute, you can let me know if
All
it's
right.
too much.
Okay. Sure. No worries. Okay.
Okay.
All right. So we'll end
Okay.
here tonight. Well, today for now. We'll just continue
Okay.
again on Monday. All right.
Okay. Thank you
Okay.
very much.
All right. Bye bye
Have a
now.
nice evening.
See you later. Bye bye now.
See you.
There we go. Okay. I forgot to share the rest of the board earlier, didn't I? So that's fine. The important thing for me here really is just as long as I get to talk and we're talking about stuff, we're good. I do have the rest of um the working that we did earlier, so that's fine. So okay, we'll end the stream here today then. But yeah, so we'll end the stream here today. But before we do, don't forget to like, share, subscribe to the channel. We are here on YouTube, Instagram, Facebook, TikTok, and Twitch when we do go live. So with that, I do hope you learned something. So I bid you all a good morning, good afternoon, good day, good evening, good night, wherever you are in the world, and stay freaky, everybody. Bye bye now.